So hopefully we are noticing that not only is synthetic division nice and easy to be able to divide these polynomials, but they do actually come in handy. So why do we care about polynomial division? Now, technically, we can do all of what we're going to be doing using long division, but that sounds like a waste of time, right? Now that we know how to do our synthetic division, it is way quicker and way easier. So when we talk about our factor theorem and when we get down there our remainder theorem, it's just way easier to do with synthetic division, right? So that is what we'll do from here on out. So a polynomial f of x, okay, has a factor of x minus k if and only if f of k is 0, aka there's no remainder. We talked about that yesterday, right? When we talked about our division, well, when we took, I can't remember what it was it 376 and we divided by 12, and we just got some nice whole number with no remainder. We said if there was no remainder, then we get to call that a factor. Now, they say instead, okay, if you plug in that k value, which would be the number that we would put in the box for synthetic division, if you get 0, then that must mean that you can divide it out the same way. So we'll get to that here in a little bit, but just kind of keep that in mind. But our factor theorem says if you get a remainder of 0, then that binomial, or I guess it doesn't have to be a binomial, but that polynomial is in fact a factor. So if you are asked to identify all factors of a polynomial, perform synthetic division with whatever number you are given. And for today, you will always be given a factor. Then what you do is you continue to factor, or you use the quadratic formula, or you use any of the factoring patterns we talked about in section 5.4, and you find the remaining factors. And then you have to pay special attention to what you're asked to find. If you are asked to find factors, we leave it in those parentheses, right? X plus 3, x minus 4, x plus 8. Those each individually, so those linear binomials, are each factors. But if you're asked to find zeros or roots or solutions or x-intercepts, you give your answers as x equals something. So you set each of those parentheses equal to 0, right? We'd get -3, +4, and -8 from those parentheses from up above. So again, just keep that in mind, pay special attention to the wording. So next, if we want to find all factors of f of x, given that x minus 3 is a factor, well, we can find all the others. So let's do synthetic division. What number is going to go in the box? Well, we set that equal to 0, and it's obviously x equals 3. So we put 3 in the box, and across the top, we will put all of the exponents beginning with whatever we have, and we're just going to go in order. So then we'll go, okay, x to the third, x to the second, x to the first, and our constant. They won't all be cubic polynomials. We just usually start with that. And then we put in our coefficients. So 2x cubed, -11x squared, +3x, and a constant of 36. We didn't need any zeros this time. And we'll perform this synthetic division. So bring down the 2, multiply 3 times 2 to get 6. And we add -11 plus 6 will give us a -5. Multiply 3 times -5 to get -15, and we add 3 plus -15 will get us -12. And sure enough, if you're noticing, when we multiply 3 and -12, we'll get a -36, which means that our remainder is 0. Now that checks out because they told us from the beginning that x equals 3 was a solution. And technically they said x minus 3 was a factor, but tomato, tomato, it's the same thing. So we know one factor. So all our factors, well, one factor is that x minus 3 that they gave us. And then what they left us with was 2x squared minus 5x minus 12. Right? Because you always lose a degree. We started with x to the third. That's how we knew we were going to have x to the second. Well, from here, now we have a quadratic. We know how to solve quadratics. That's what all of chapter 4 was about. Now, this one is going to be factorable. If it was not, you can always use your quadratic formula. But let's factor this one. And we'll use divide inside. So 2 times 12 will give us 24. Numbers that multiply to 24 but subtract to give me 5. Let's see, 1 and 24, 2 and 12, no, 3 and 8. So then I'm just going to hold off on that x minus 3. I'll bring it along at the very end. But we've got x and 3 and x and 8. So we're just factoring this guy here. My signs are different. My bigger number is negative. X minus 8x plus 3. And we divide and slide by that coefficient of 2. It does not divide nicely from that 3, so 2x plus 3. But that 8 over 2 just becomes an x minus 4. So all of our factors are going to be, let's bring that x minus 3 back. So our final answers, x minus 3, 2x plus 3, and x minus 4. Now obviously order does not matter in this case since we are just multiplying, but those 3 are all of our linear factors. Now example 3 is very similar, but this time we're asked to find all roots of p of x. So notice they're giving us fun new names for our functions in different function notation, but nothing else changes. So they tell us x plus 5 is a factor, so that means that negative 5 is going to be our number in the box. Across the top, let's see, I'm starting with a quartic polynomial, so x to the 4th, x to the 3rd, x to the 2nd, x to the 1st, and our constant. Our coefficients are 1x to the 4th, 5x cubed, no x squareds, so there's our 0, watch out for those. Negative 8 in front of our x and negative 40 as our constant. Bring down your 1 and multiply. Negative 5 times, bring it down actually, there we go. Negative 5 times 1 is a negative 5, and we add 5 and negative 5 gives us 0. Negative 5 times 0 is 0. We add them up, we get 0. Negative 5 times 0 is 0 again, but this time when we add negative 8 plus 0, we get a negative 8. And we multiply negative 5 times negative 8, sure enough, is a positive 40. So when we add negative 40 and 40, our remainder is 0. Now, again, we expect a remainder of 0. If you don't get one, you should have some red flags. So far, we knew x plus 5 was a factor. And now we know, okay, we started with x to the 4th, so 1x cubed, 0x squared, 0x minus 8. Oh, okay, x cubed minus 8 is our other factor. However, x cubed minus 8, hopefully you're noticing that that is your SOAP pattern because x cubed is a perfect cube, as is 8. So we'll bring that x plus 5 with us this time. And then let's think of that SOAP pattern. So before we do, notice that x would be the cubed root of x cubed, and 2 is going to be that cubed root of 8. So when we use our SOAP pattern, remember that your first term just goes first, and your last term just goes last. Your second set of parentheses, it's your first squared, you multiply the 2 together, so it'll be 2x, and then it is your last squared. 2 squared is 4. Then our signs, let's see, we had a minus, so it's going to be the same, the opposite, and always positive. Now, we're asked to find all of our roots, though. Here are all of our factors, so if they asked us for factors, we'd stop here. Finding our roots, though, we are going to need to set these equal to 0. Well, we can start to do that pretty quickly. So if we have x plus 5 equal to 0, subtract 5 from both sides, x equals negative 5. X minus 2 equals 0, we add 2 to both sides, and x is positive 2. Now, using your SOAP pattern, that second quadratic trinomial, right, the longer set of parentheses, will never be factorable, so don't fall into that trap. We will, however, be able to use our quadratic formula. So x equals, let's see, a is 1, b is positive 2, and c is positive 4. X equals negative b plus or minus the square root of b squared, 2 squared is going to be 4, minus 4ac all over 2a, which is just 2. So x equals negative 2 plus or minus the square root of, okay, PEMDAS says do that multiplication first. So 4 minus 16 all over 2. 4 minus 16 reduces to 12. Negative 2 plus or minus the square root of negative 12 all over 2. Okay, first of all, we've got a negative under the square root. So we should immediately take that out and call it I root 12. But we get to break down the square root of 12. So the square root of 12, we can break into the square root of 4 and the square root of 3. The reason we do that is because the square root of 4 is just 2. So x equals negative 2 plus or minus 2I root 3 is how we'd write all that. All over 2, but of course we're still not done because out of all 3 of these terms, we can take out a 2. So that becomes a negative 1. This just becomes an I root 3, and your denominator just becomes 1, so we don't even need to bother to write it. So our final answers are negative 5, positive 2, and negative 1 plus or minus I root 3.